Okay. Hi, everyone. Welcome to the 22nd ECS and Cloud Feedback Virtual Symposium, going for a while now. The format that we will be having 3 12-minute talks. There's going to be some time for questions after each talk, and then if we have time at the end, we'll have a short general Q&A at the end. So if you have any questions for any of the speakers, you can just type them into the chat at any time. Or if you'd like to ask the question directly, just raise your hand and we'll unmute you. You can ask the question. And we're always on the lookout for speakers, so please get in touch with anyone on the executive committee if you're interested in giving a talk. You can find information about how to contact us, as well as videos of past events, lots of other information at our website, which is here. And you can also see the slides from Xiangping's talk from last week last session that had some technical difficulties. Those are up on the page for the last symposium meeting. So with that, let's move on to our speakers. We have 3 great talks today. Our first speaker is going to be Bosong Zhang. Bosong is a postdoctoral research associate at Princeton GFDL. And maybe Bosong, if you can put up your slides.
Sure.
And Bosong is going to be talking about exploring the SST pattern effect on climate feedback and climate sensitivity in GFDL models. Take it away, Bosong.
Okay, thank you, Jonah. So hello, everyone. I want to thank the organizers for this opportunity to share my work at GFDL Princeton. And I also want to thank my co-authors for their help in this project. So today I'm going to talk about the SST pattern effect on climate feedback and climate sensitivity in GFDL models. So here is the outline. First, I'm going to talk about the SST pattern effect in M4 using a Green's function approach. Next, I'm going to talk about how the spatial pattern of incoming solar radiation will affect climate feedback and climate sensitivity in an atmosphere and ocean coupled model. And then I will give a quick summary. So let's start. Previous studies have applied the Green's function to atmosphere models like CAM4 and CAM5. And the Green's function basically assumes a linear combination of the responses to SST perturbations at all ocean grid points, which is represented by the equation here. And motivated by this, we are following this approach and try to do the idealized SST patch experiments using the most recent GFDL M4 model. Here, the 2 figures show the location of the idealized SST patches. With these experiments, here are some key results. So in general, our results are consistent with previous studies. For example, if you look at the net UV radiation in response to SST perturbations, you can see over the deep convective regions like the Western Pacific, there are very strong radiative cooling associated with in response to the SST warming. However, one thing we find is that the response is sensitive to the amplitude and the sign of SST perturbations used in the idealized SST experiments. As you can see, with different amplitude like 1.5 Kelvin, plus 4.0 Kelvin, and negative 4.0 Kelvin, the global mean responses of net UV radiation varies to some extent. This does suggest that the Green's function is sensitive to the amplitude of SST perturbations. And the second point is that we find that the performance of the Green's function is sensitive to the integration time. As you can see, the orange lines are using the 10-year simulations, whereas the blue lines are using the 30-year simulations. You can see there are some differences across these reconstructions. I think Block Johnson is leading a Green's function MIP project to further address these issues. For this results, this has been published in the Journal of Climate. There are more details you can find there. And if you want to look at the Jacobian matrix from these experiments, you can find here on the GitHub or reach out to me. So we already learned that the spatial pattern or SST is important to climate feedback. A natural question is, what's the role of spatial pattern or radiative forcing? So there has been some progress in previous studies. For example, variations in obliquity can affect the spatial pattern or SST, the large-scale circulation, and the climate feedback. And we also learned that absorbing aerosols can modify the spatial pattern or radiative forcing, like by William et al. 2022. And also, the CO2 radiative forcing has both local and remote effects. And from the Q flux perspective, previous study have shown that the spatial pattern of ocean heat uptake can affect the climate feedback and climate sensitivity. In addition, there is strong connections between the tropics and the extratropics. So, motivated by these studies, we try to explore the impact from the spatial pattern of solar radiation. Specifically, here the question is, how does anomalous incoming solar radiation will affect the spatial pattern of SST, climate feedback, and climate sensitivity? So to address this, we do the experiments in a coupled model. Anomalous incoming solar radiation are added over the entire globe, or the northern hemisphere, the southern ocean, or the tropics. So we do the experiments with both positive and negative perturbations. So here, the top row shows a shortwave radiation, shortwave downward radiation at top of atmosphere with positive perturbations, and the bottom row shows negative perturbations. So here, I want to stress that even though the spatial patterns or radiative forcing varies between these experiments, however, the global mean values is the same. For example, for the positive solar radiative forcing, the global mean value is set as +4 watts per meter squared. For the negative ones, the global mean values is set as -4 watts per meter squared. So the same global mean value, absolute values, but different patterns. With these experiments, we can look at the climate response. So first, let's look at the evolution of the global mean surface air temperature. Here, solid lines are for the positive perturbation experiments, and the dashed lines are for the negative perturbation experiments. As you can see, near the end of the simulation, the Southern Ocean +4 case induces the greatest warming among these experiments, whereas the tropics +4 induces the least amount of warming. So given the same amount of forcing, the climate response is very different across these simulations. This does suggest that the climate response is sensitive to the location of the forcing. Next, let's look at the spatial pattern of SST. Here, this figure shows the SST patterns average over the last 50 years of each simulation minus the control simulation. So as you can see in panel A, for the global uniform positive forcing, there is an overall warming, and also there is enhanced warming in the Arctic regions. For the Northern Hemisphere case, it's not surprising that there is enhanced warming in the North Pacific, but also there's warming in the Arctic regions. When it comes to the Southern Ocean, we found it's surprising that there's very large warming appears over the Southern Ocean. Also, you can see that there is warming in the tropical Eastern Pacific and tropical Atlantic, and also some Arctic warming there. So this pattern does suggest that there's tiny connections between the Southern Ocean and the ocean in the tropics. This has been previously reported in experiments such as pacemaker experiments. In comparison, if you look at the tropical plasma case, you see the signals are much weaker, even though it shows an overall warming pattern. So this different SST patterns and the global mean responses, we are wondering, is the SST patterns is associated with the global mean surface air temperature response. Naturally, since we already have the Green's function, we further use the Green's function to reconstruct the global mean surface air temperature. Here in this figure, the black solid lines are for the model output, and the red solid lines are for the Green's function reconstruction. As you can see across the experiments, the Green's function in general did a pretty good job in reproducing the model outputs. However, if you look at the Northern Hemisphere case, you do see that there is more bias. So one possible reason is that the Green's function does not account for the temperature change over land, which may lead to the more biases for the Northern Hemisphere case. Moving forward, we further compare the radiative forcing and radiative feedback across the experiments. Here, the top panel shows the radiative forcing, and the bottom panel shows the radiative feedback. As you can see, the absolute values of the forcing are almost the same across the experiments. However, if you look at the radiative feedback, you do see large variations across these experiments. The Southern Ocean case gives you the least negative feedback, but the tropics give the most negative feedback. So these results indicate that feedback exhibits dependence on the location of the forcing. So here are some take-home points. A Green's function approach has been applied to the M4 model to show its SST pattern effect. And further, we explore the special pattern of radiative forcing, how it affects the SST patterns and the climate feedback, climate sensitivity in a couple model. We find that even given the same amount of forcing, the Southern Ocean +4 induces the largest warming, while the tropics +4 induces the least amount of warming. This suggests that the climate response is sensitive to the location of the forcing. And there's also both local and remote impacts, like in the Southern Ocean case, you'll see warming not only in the Southern Ocean, but over the tropical Eastern Pacific and tropical Atlantic, and also the Arctic regions. So for the first part of this project, this has been published in the Journal of Climate. There are more details. And for the second part, it's in preparation. And that will be all on my talk today. Thank you very much.
Thanks, Bosong. That's a really clear talk. Does anyone have any questions for Bosong? Not seeing anything. Yeah. Oh,
I had one clarification question. I didn't quite follow when you do. So you do the solar output perturbation experiments. So it's 4 watts per square meter globally, and then when you do the regions, are you making the perturbations in those regions much larger so that if you average over the whole globe, you still get 4 watts per square meter?
That's correct. If you look at the color bars here, when you add it regionally, the magnitude is slightly larger to make the global mean the same across experiments.
Okay, that was my question. Thanks.
Okay, thank you.
and I saw Aura put up their hand.
Oh, sorry, that's Robert Pincus.
Oh.
That's set to my daughter. I wonder, Bosong, if you looked at this in like an effective radiative forcing framework, if you would have the same dramatic changes. Yeah, you're looking at stratospheric adjusted forcing, but of course the stratospheric adjustment is going to be very almost irrelevant to solar forcing. Stratospheric temperatures are going to adjust mostly globally into CO2 forcing. You know, you could do fixed SST, or you could maybe look at this with regression. There would be a couple different ways to do it, but I just, you know, we understand that the instantaneous radiative forcing is not the thing that matters for temperature change, but rather the effective radiative forcing that encompasses all the adjustments. And so the stratospheric adjustment is one piece of that, but there are all the other adjustments related to changes in circulation. So for me, it would be really interesting to know if you went to a full effective radiative forcing framework. One question would be, how different are the effective radiative forcings based on the location? But the other would be, do these large magnitudes and feedbacks persist?
Yeah, that's a very good question. We do see there are some like variations between the different periods of the simulations. The feedback, as you know, is not a constant over time. But yeah, the effective radiative forcing is a very good suggestion. I will investigate this and looking more, try to analyze the results in more details. Thank you, Robert.
Okay, and then we had a question from Nader.
Hi, Bosong. Thanks. Just thinking about the Green's function approach, which you used in both parts of your talk, it seemed to work fairly well for these regional forcings that you imposed. But I'm remembering from your paper that there were some coupled model simulations, I forget if it was historical or abrupt 4X, where it didn't seem to work as well. You also noted in the first part of your talk that there's a sensitivity to the amplitude and sign of the perturbation, which sort of signals some kind of nonlinearity. So can you comment on that?
Sure, Nader, that's a good question. So here, for this plot, I'm using the Green's function from the 30-year simulation with 1.5 Kelvin perturbations. And here I didn't do the significance test, basically, which means I didn't remove all those kind of the so-called noises. Here, my comment is that for the Green's function may have some issues in terms of reproducing simulations with relative uniform warming, like the 4-time CO2 experiment. But here, let's say for the Northern Hemisphere, Southern Ocean tropics, if you look at the ST patterns, it's not that uniform, right? There's still large spatial variations. You do see some patterns there. So the Green's function here does capture these global warming responses, but there should be some caveats. So I would say this is more like a qualitative assessment instead of like quantitative analysis.
I see. So you might expect that, in these strongly patterned cases, you might expect the Green's function approach to do better.
Yeah, exactly.
Non-linearities to matter less. Okay, thanks. Appreciate it.
Thank you, Nader.
Okay, thanks. I think we should move on to the next talk, but maybe Sheng Lei, if you could put your question in the chat. And Bosong, please keep an eye on the chat.
Oh, sure. Thank you.
Thank you, Bosong. That was a great talk. Our next speaker is Jing Feng, who is also a postdoctoral research associate at Princeton GFDL. But she's going to be talking about something different. She'll be talking about how a stable long-wave feedback is maintained under global warming. All yours. I think you're...
Can you hear me well? Thanks.
Yes, now we can hear you.
So good morning, and thanks a lot for this exciting opportunity to present my work here. So today in my talk, I would like to propose a simple theory to explain the clear sky long wave feedback. So our climate system is maintained by a delicate balance between the net incoming solar radiation and outgoing long wave radiation at the top of the atmosphere. External forcing from the sun or from gas emissions can lead to extra energy in the system, which heats up the climate. So in this global warming process, radiative feedback parameter alpha is used here to quantify the rate that extra energy can be removed per degree of surface warming. A negative alpha means that the climate system is stable because it can restore a new equilibrium climate state known as the ECS. So the magnitude of feedback poverty has been evaluated by many studies. For Thermips's model, a about 4 times CO2 experiment, the feedback has been quantified as -1 watts per square meter per Kelvin, which means that for a 4 watts per square meter of CO2 forcing, the global surface warms up roughly by 4 Kelvin to reach an ECS, and the system is stable. The stability largely comes from the Longwave OAR spectrum, which appears to be dominated by the clear sky radiation process without the impact of the cloud. So as the stabilizing agent of the climate, the clear sky long wave feedback is extremely important. If the clear sky long wave feedback becomes positive, then the climate will get warmer and warmer without any control. So what controls the OAR? In a clear sky condition, OAR sources from the surface and the atmosphere. The surface emits at a rate controlled by Planck function of temperature and then transmitted through the atmosphere. Because the atmosphere contains greenhouse gases, it traps energy from the surface and then emits thermal energy back to space. This large tau S marks the total transmittance of the atmosphere, and the OAR ADM marks the energy that directly sourced by the atmosphere. We can then have a deeper look of the OAR by breaking it down into the infrared spectrum, as shown in the left figure in the color blue. Higher values in the spectrum compared to the dashed curve in the background means that the atmosphere is transparent to greenhouse gases. And those spectral ranges is called infrared window, and the OAR in infrared window is largely controlled by the temperature of surface. Other spectral ranges are sensitive to absorption of greenhouses, such as water vapor, CO2, CH4, NTO, and ozone. And these absorption bands are more sensitive to emissions that sources from the atmosphere. With 4 Kelvin of surface warming, OAR increases. The largest visible differences are in the infrared window, where the surface warms and emits more energy. And this emission can be effectively lost to space because the atmosphere is transparent. So analytically, the feedback can be broken down into a surface and atmospheric term. And the surface term accounts for the partial radiative perturbation in surface temperature, governed by Planck function and the transmitted through the entire atmosphere. So based on this dominant contribution from infrared window, recent studies have elucidated that the surface term dominates the long wave feedback process. Implies that once the infrared window is narrow by enhanced water vapor absorption with a warming climate, feedback becomes close to zero and unstable runaway climate may occur. We then show the actual global mean long wave feedback spectrum in red. By differencing the 2 OAR curve in the blue, we find that the surface feedback is -1.3, and this magnitude is consistent with the surface temperature kernel in the publicly available dataset. The total is -1.8, consistent with existing feedback literature. And the difference is at -0.5, comes from the atmosphere, from the absorption channels, and takes about 35% of the total, and is indeed smaller than the surface term. But if the surface term always dominates, as shown here, then wouldn't we expect to see a less stabilizing feedback in a warmer climate because the window is less transparent at that time? So to test if this is true, we show the mean feedback for areas that are warmer than 290 Kelvin corresponds to roughly 40% of surface area on Earth. In this region, feedback in the window channels have been reduced compared to the global mean, but the total feedback remains the same. This is really because the atmosphere feedback becomes more stable to -0.8 and become comparable with the surface term. Therefore, the atmosphere feedback is quite critical in a warming climate, and it's important to know why it is a stabilizing process. And to further understand the source of the atmosphere feedback, we divide the absorption channels into bands that are more sensitive to water vapor and bands that are more sensitive to other greenhouse gases, and integral the atmospheric feedback in the two spectral ranges separately. This figure shows the atmospheric feedback and its component in two spectral ranges as a function of local surface temperature. So we find that the atmospheric feedback sources half from water vapor and half from the sum of all other greenhouse gases. And the atmospheric feedback is less negative in polar regions and becomes more stabilizing when surface temperature increases. It reaches up to 0.9 in the tropical regions. So compare with the global mean sea surface temperature at 288 Kelvin, our global climate is stepping into a regime where the atmospheric feedback process becomes more and more important. So in the next couple of slides, I will explain why water vapor and other greenhouse gases induce a stabilizing feedback process. So let's consider an idealized case with uniform lapse rate and vertically uniform warming. The atmospheric emission to OR comes from this blue line in the temperature and transmission coordinate. Temperature controls the Planck source function, and the transmittance controls emission and absorption of the atmosphere. By adopting the classic strong line approximation, we know that the transmittance of a gas absorber over a band is jointly determined by the partial pressure of this absorber, forming air pressure and the temperature under the pressure broadening effect in Earth's troposphere. In the case of well-mixed gases, by definition, partial pressure is proportional to air pressure, which is exponential to temperature according to the ideal gas law and hydrostatic balance, meaning that the transmittance of a certain layer is just proportional to air pressure. So if the surface warms up by 1 Kelvin, we expect to see the line in transmittance temperature space to shift left by 1 Kelvin. And this shifted temperature is marked as delta T sub B. And the difference between the two lines marked in the shaded area after integration equals to the atmospheric feedback. And it is proportional to delta T sub B. And for water vapor absorption, the same logic still applies. Although different from well-mixed gases, the partial pressure of water vapor is determined by temperature following the Clausius-Cropper equation for a given fixed RH. So without considering the dependence of foreign pressure, the two lines shown here should overlap each other perfectly. And because of this foreign pressure dependence, the line would have to shift left, and the magnitude of delta T sub B would depend on the relative importance of foreign pressure and vapor pressure. It can be analytically solved if lapse rate and surface temperature are given. We find it equals to 0.15 Kelvin in strong absorption lines of water vapor. A more complex model is presented here in our preprint to account for the overlap between different gases in the realistic atmosphere. And the top panel shows the actual minus temperature changes in OAR with 4 Kelvin of ECS warming in the blue curve. And the red curve shows a theoretically derived delta T sub B caused by the atmospheric emission changes during the process, and overlap with the blue curve very well in the absorption channels. And in strong absorption channels of water vapor, you can see that delta T sub B is indeed 0.15 Kelvin that I marked with the black dashed line. Because the water vapor absorption spectrum is so broad, delta T sub B in absorption channels of other gases are reduced to around 0.15 Kelvin to 0.6 Kelvin due to the overlap with water vapor absorption. And strong water vapor absorption bands contribute to a greater fraction of OAR. As a result, the two spectral ranges can contribute to equal half of the atmospheric feedback. So next, we use the delta T sub B from the top panel to compute the atmospheric feedback for the red curve in the middle panel and compute the sum of the atmospheric surface as a total in the color yellow. And the blue curve is the actual clear sky long wave feedback when ECS is reached using lambda line rated models. And our theory reaches a good agreement when compared to the expensive and accurate lambda line models. We also found that after spectral integration, the theory explained the spatial parting clear sky long wave feedback quite well. It reproduced the more stabilizing clear sky long wave feedback from poles to subtropics and the less stabilizing feedback from the subtropics to tropics that are driven by relative humidity changes. And the key message here is that the zonal mean shape of the feedback is dominantly controlled by the atmospheric turn that we have addressed in this study. So in the end of the talk, I would like to summarize some key points here. So we show that an atmospheric feedback process that sources from greenhouse gases is stabilizing our climate, and it is quite critical in a warming climate where infrared window starts to vanish. A large portion of this stability comes from the pressure broadening effect on water vapor. The symbol model proposed here achieves quantitative accuracy because we account for the pressure broadening effect. And we account for the spectral overlap between different gases. And at last is the take-home message that I'd like to convey to you who are interested in feedback analysis. So this pressure broadening effect is largely the reason why water vapor feedback does not completely offset the feedback from atmospheric temperature. So our theory provides a way to comprehend the results from advanced feedback analysis studies. So for more details of our theory and its implications, please check out this preprint and send me a message afterwards. So with that, I'm very happy to take questions. Thanks.
Thanks, Jen. That was great. Does anyone have any questions? I see there's a lot of activity in the chat for Bosong, but does anyone have questions for Jing? Oh, there's a question from Chenggang Wang. Chenggang, if you want to unmute.
Yeah, hi, Jing. Thanks for the talk. I just have quick questions that so since the carbon dioxide takes approximately the same role as the water vapor to stabilize the feedback. So given the CO2 emissions more, and so CO2 concentration is more in the atmosphere in the future, we expect that actually compete over the water vapor?
Yeah, that's a great question. So just to give you some hint, because we don't run an idealized simulation into a further warmer climate. You can see that in the hotter range of the Earth, it's actually water vapor and CO2 still take similar portion of the feedback. And this is really because there's kind of a masking effect between CO2 band and water vapor, because this side of CO2 is overlapped with water vapor. So in a warmer climate, you have stronger water vapor absorption, and this band kind of extends and have a stronger impact on CO2 as well. So we have tested that in the tropical climate, if we remove CO2, we can still get like 90% of the feedback in atmosphere. So to your question, that we expect there are some roles by CO2, but not as strong.
I think. Thank you.
Hey, Tim, I think you were next.
Hi, Jing. Great talk. And I want to come back to this zonal mean plot at the end and ask about what's the role of the inhomogeneous vertical temperature change? Is that irrelevant?
Yeah, that's a very nice point. So yeah, it is quite relevant. From the polar regions to the subtropical regions, there's a tremendous increase of the feedback, and you can see that as in the atmosphere. So in the conventional feedback analysis, it's just a part of the lapse rate feedback. So you have a more top-heavy warming in the subtropics compared to tropical regions, and in the tropical regions, you have a stronger warming near the surface. So this part as comes from the atmosphere. And if we break down into the spectrum, it comes from the absorption channels, and then we attribute them as part of the so-called atmospheric feedback in the study. So in other words, the lapse rate feedback from the polar regions to the tropical regions works to enhance the atmospheric feedback when it comes to a hotter climate.
Can I ask a quick follow-up, Jing? When you're showing this zonal mean feedback, are you dividing by local temperature change or by global mean temperature change?
By local temperature changes.
Okay, thanks. Dennis?
Yeah, yes, Jing, nice talk. Could we go back to the plot where you're showing the division between the greenhouse gases and water vapor split in two? And I was noticing that the plot levels off at around 295 and then doesn't change before you really get to tropical temperatures. Can you explain why that is?
It's a really nice observation. So it is because the humidity in the base state are different. So in the control state, this region goes into kind of the so sorry, let me think about it. So from 295 to 300, this is the drying regions. So we have the humidity decrease.
So this is the actual temperatures of the atmosphere, not some theoretical one-dimensional profile.
No.
I see.
So I should have to make it clearer. So to make this plot, we extract different locations from the control run of our GFDL CM3 model. So, and then we composite different locations on the globe to make this plot. So there are differences in the background humidity and temperature structure. So this is not an idealized results.
Thank you.
Okay, I think we might as well just move on to Dennis.
Thank you.
Thanks a lot, Jing.
All right, thanks very much for this opportunity to, here we go. How am I doing?
Looks good.
You're great.
Okay, yes, so this is a brief talk about paper I wrote last summer suggesting that the Antarctic ozone hole could have something to do with a pattern effect on climate sensitivity. You can read the paper, open access in PNAS if you're interested, but there's only about 3 figures, so I should be able to cover it here today. Also, I'm not a postdoc at GFDL, but I was a graduate student there, so maybe I fit into this session somehow. So first, I'm going to review some of the suggestive simulations that prompted me to think about this. And then I'm going to show the observational evidence that strong zonal winds over the Southern Ocean can feedback to produce, first of all, a cold Southern Ocean, then a cooler East Pacific. And then suggest that there's a possibility that the jet shift associated with the ozone hole could have contributed to the La Nina drift that we've seen over the last decades. And then at the very end, if there's time, I'll show you some more recent observations that are very intriguing. Okay, so this is the thing that we've been trying to understand. We've heard a lot of talks about this in this session. At first glance, it kind of looks like the La Nina response. It's cold in the eastern equatorial Pacific, and you've got those 2 warming lobes that are associated with the Rossby waves propagating away from their source in the far western Pacific. But there are some odd things about it. Relative to the El Nino response, the Southern Ocean cooling is much, much bigger. And the equatorial, the tropical response in the eastern Pacific near South America is displaced southward of the equator. So maybe some hints that either there's some longer range feedbacks involved here that we don't fully understand, or that maybe there's a southern hemisphere source for this peculiar warming pattern in the last 40 years. And this is just showing you the regression of a Nino 3.4 ENSO index onto the global air temperature, I think it is, probably not sea surface temperature. And you can see that there's a large equatorial signal here and then some smaller cooling in the southern hemisphere. And what we see in the trend is a much larger cooling in the southern hemisphere and more displaced toward the Drake Passage and South America. So my first thing that I can remember that stimulated me in this direction was this paper by Machoso et al. I think it's in 2016, where they were thinking about the double ITCZ balance, and maybe we could get rid of that by getting a proper amount of shortwave cloud reflection over the Southern Ocean. So they just cooled the SSTs, or they reduced the absorbed solar radiation over a band of the Southern Oceans. And in this case, they looked at two models, the UCLA GCM and the NOR ESM. And the UCLA GCM produced this interesting pattern that we've talked a lot about, where not only does the Southern Ocean cool, but also the equatorial Eastern Pacific. And on the bottom here, you're seeing the sea level pressure pattern associated with that, with this high pressure over the subtropics of the Southern Ocean, which helps to produce the connection between high latitudes and lower latitudes, because it both produces stratocumulus reflection over here, which they argued was important in producing the connection. It also produces a circulation which moves colder air toward the equatorial Eastern Pacific. That was followed up by a more extensive study that Sarah Kang talked about in this series a while back, where they did a more extensive list of models and confirmed that it was the response of the low clouds in the off the west coast of South America and Chile that was kind of critical for producing the connection. And then more recently than that, there was a paper by Yue Dong et al., which I think was also discussed in this session, where they argued that there is a two-way feedback between the tropics and the Southern Ocean. If you, in the upper panel here, they're cooling on the equator in the Eastern Pacific, and that produces a cooling in the Southern Ocean. And if you cool in the Southern Ocean, you also produce a cooling in the Eastern Pacific. So there's a mechanism that connects these two, at least in this particular model, but from the previous paper, it seems like many models are able to simulate this connection. So I got the idea then, well, the winds at 60 South have increased over the last 40 years. People believe mostly because of the ozone hole. And using sort of the classical idea from a 2002 paper that, well, if you have stronger winds, you get Ekman transport toward the equator, and maybe that cools the Southern Ocean. If you can cool the upwelled ocean water fast enough on the polar edge of that, which is going to be a question. So we've had this wind increase, and I wanted to see observationally what I could do about connecting those two things together. So all the data I'm showing here are monthly means, and I'm going to focus on the October to March season. I'm going to use ERA 5 winds and sea surface temperatures from 1979 to 2021. October to March season works better, the argument being that's the end of the ozone hole, and it's also the season when the Southern Hemisphere is more zonally symmetric. So I make a Southern Annular Mode Index from the difference between the zonal mean wind at between 40 and 60 South. So I take the 55 to 65 South average and then subtract the 35 to 45 degrees South average. A similar index based just on 60 degrees South zone wind does not give quite as clear a signal. So maybe the wind stress curl is a factor here. I'm just speculating. So to make a reasonable job of this, we have to remove the very strong direct connection between ENSO and the Southern Ocean. So what we do is to remove by linear regression the Nino part of both the global sea surface temperature and our SAM index by regressing them against Nino 3.4 and removing that. If you don't do that, you get a very strong signal that looks just like ENSO. And then we composite times when this SAM index is either +1 or -1 standard deviations away from its mean value, and then plot the difference, and we get this result here. So you produce a pretty strong cooling over the Southern Ocean, particularly upstream of the Drake Passage, where we're consistent with the trends. And you also produce a smaller but statistically significant cooling south of the equator in the Eastern Pacific in that kind of triangular shape that the previous modeling papers were producing. So at this point, oh, I think I went the wrong direction. So looking at that figure, we seem to have successfully removed most of the ENSO signal. The Southern Ocean cools in response to SAM pretty strongly on monthly time scales, particularly in the Southeast Pacific. And this tropical response south of the equator in the Eastern Pacific is statistically significant, maybe communicated through the atmosphere, since it's apparently a fairly short time response. So question would be, we've used monthly data, so pretty high frequency data to get this signal, but some of the models suggest that after a while, the upwelling of warmer water from below will defeat this cooling signal associated with the Ekman drift. But of course, that's a very difficult problem for ocean models to do, I think, because you got this very shallow fresh layer that you have to simulate properly. Yeah. So another piece of evidence that I think is interesting, maybe bears more looking at, was this paper by Liao and Chow in, I think it was 2017. And what they did was take the GRACE gravity data, compute the first EOF of the ocean bottom pressure inferred from that, compute the geostrophic currents associated with that. And then on the bottom left here, they're plotting the principal component of that gravity EOF against the Southern Annular Mode Index. And you can see that there's a nice, reasonably good correlation between the two. And what that produces is a much stronger and more poleward Antarctic circumpolar current in eastern Antarctica, which kind of breaks down over the Pacific Ocean, but it breaks down into kind of a gyre circulation where you have poleward flow over here next to that feature, which I can't remember the name of, and then an equatorward flow just upstream of the Drake Passage. So there's a little bit of a gyre that develops here. And maybe these currents are helpful, at least on some long time scale, in terms of bringing colder water toward the tropics. I don't know. It's just kind of speculation on my part based upon this observational evidence. So that's kind of the summary of my paper. And now I want to go on and talk about some data I was looking at last week. So this is a plot of the global mean surface air temperature from a NOAA reanalysis data set plotted from 2002 to 2022. And you can see there's this interesting jump of about 0.3 degrees Kelvin right around the time of the 2015 El Nino event. It'd been the first El Nino event for a while. And it's interesting to look at the spatial structure of that step in global mean surface temperature. Actually, this is the trend since 2002 to 2022. And the interesting thing to me is that this pattern of cooling in the Pacific and cooling in the Southern Ocean has persisted through that global warming jump. The temperatures have warmed most in the Northern Hemisphere and most over tropical land areas and the maritime continent over there. But the equatorial Eastern Pacific and the Southern Ocean Pacific have continued to cool. It's quite an interesting observation, I think. And here's a plot of the wind at 60 degrees south between 1970 and 2020. There's no obvious jump associated with the ozone hole, I guess, but it seems to have, although it's a very noisy signal, the blue line is the individual monthly means and the red line is a low pass filter of that. It does seem to be creeping upward slowly with time. This is the wind at 10 meters. So going from 3 to 5 is probably a pretty big deal in terms of wind stress, et cetera. So I think this continues to be a very, very interesting problem that we need to try to figure out. It's very interesting, I think, ocean atmosphere coupled phenomenon. This is the trend in the zonal winds from 1970 to 2022 for the annual mean. And in the annual mean, there's a pretty strong signal in the Southern Ocean winds increasing over this period by some substantial amount. And there's also a corresponding weakening in the trades north of the equator in the Eastern Pacific, and some additional convergence over the maritime continents associated with the tropical precipitation gradually shifting westward over this period. Okay, I think that's all I got. I think I finished in plenty of time, so we have time for questions, I hope.
Yeah, that's awesome. Thanks, Dennis. I saw in the chat, Andy mentioned that it's not too late to be a postdoc at GFDL. But I guess I maybe want to take the convener's privilege to ask, you know, I really enjoyed reading this paper. I thought it was really provocative. But I guess what I'm wondering is, like, what part of this mechanism do you think would be poorly represented in climate models? Because, you know, that seems to be the biggest issue, is the fact that the models aren't giving this cooling trend.
Yeah, so if you think it's starting in the Southern Ocean, then it might be the response of the Southern Ocean to the wind shifts or to global warming. It's really a question for the ocean modelers to ask them how accurate they think their models are in terms of representing the response of currents and circulation to wind, or the freshening of the Southern Ocean associated with enhanced precipitation or enhanced melting, possibly. I think there are some pretty delicate thin layers down there that would be critical for getting the right temperature response in the Southern Ocean. So that's where I would blame it on the oceanographers or the ocean modelers.
Great, yeah. I think Gavin put the same question in the chat. Does anyone else have a question for Dennis? Or Rob, do you want to unmute?
Hi, Dennis. Thanks for the talk. Following up along the same lines as Nick's question, this analysis you're showing here in this figure 3 is something you could do in models as well. So have you done this or seen any papers that do this, and see if, like, how different is this SST response to SAM in models?
No, I have not. Well, it seems like a straightforward thing to do.
Mhm. Anything else? Swart.
Yeah, it's Neil Swart here. Yeah, I'm just curious about this connection to stratospheric ozone depletion in the March to October season, because from my understanding, most of the papers that have looked at the significance of ozone depletion on wind strength or position changes really show that effect is largest in DJF. And when we go into austral winter JJA, there's quite a strong greenhouse gas effect or CO2 effect, let's say. So I'm just wondering, when we're averaging over March to October, how much is the influence of ozone depletion versus greenhouse gases, let's say?
I don't know the answer to that question, but the modeling work that I'm familiar with suggests that at least so far, the ozone hole has been the dominant influence on the poleward shift of the winds over the southern hemisphere. Of course, that could be wrong too. Some people argue that the response in the tropics is actually a forced response. And if there's a forced response in the tropics due to global warming, then one might then expect via this two-way coupling that's been explored in models that the Southern Ocean would also respond. So it might be the seasonal response of the zonal wind might be a clue as to what the ultimate source of the wind shift would be.
Okay, thanks. Yeah, I think I find it's easy for people to get the wrong idea, because virtually every modeling paper that's looked at stratospheric ozone impact focuses only on DJF, because it's the only real season where the signal is significant. And if you look on the annual mean or in JJA, it's actually quite a different story. So yeah, Anyway, thanks.
Thank you.
Okay, we probably have time for one more question.
I guess the other thing is that October to March is the summer season when things might be a little bit more zonal and less stirred up. And the ocean's a bit more stratified, maybe.
Does it concern you, the time series, the fact that there's no obvious, sign of the ozone hole or of the recovery of the ozone hole?
I think that's interesting, isn't it? I guess what my results suggest is that zonal wind variations over the Southern Ocean can produce a cooling that has the shape I'm showing, irrespective of the source of that wind increase. And as I plotted the zonal wind, there's no, Gavin Schmidt is showing something in the chat there, which I can't see.
He's saying October to March is looked at by Miller et al. In 2006.
So having said that, I realize now it's actually November to February. So I apologize for getting confused there. Sorry.
There's a definite jump.
Tim Merlis writes in the chat that the annual mean direct response to CO2 is a positive SAM. There's a Menzel and Merlis paper from 2019, which showed that.
Yeah, the global warming simulations generally show a poleward shift.
Yeah.
depending upon how sensitive the SAM mode in the particular model is to greenhouse gas warming.
Okay. Well, I have to go teach. I think Andy left and Christy as well. Thanks so much, everyone. Thanks to the presenters for a really great series of talks. And we'll see everyone next month.
Cheers.
Thanks, Dennis.
Thank you.
Thank you.